So in this problem, we're given a situation that looks something like this. Now remember, you're going to want to draw a picture of every situation as it comes up if you're not given one already. So here we have a block that's attached to the wall by a spring of spring constant K2, and that's being pulled from the other side by a spring of spring constant K1. We are given that K2 is equal to 2K1. And what we're asked is that if K1 is stretched to a distance d, that means that the difference between its current length and its equilibrium length is d, not that its total current length is d. What is the stretch in the spring K2? And so what we're going to do is we're going to draw an isolation diagram for this block right here. And the reason we're going to do this for the block is because that's the point where these two forces are essentially meeting. It's going to give us a relationship between the spring force from K2 and the spring force from K1, and that's going to allow us to relate them and find an answer. So it's being pulled to the left with the force K1 times D. D is the stretch, remember, in spring number 1. It's then being pulled to the right with some force K2 times delta X2. Delta X2 is the stretch in spring number 2, and that is what we're going to be trying to solve for. Now, what's really important to look for is this word equilibrium. In the problem statement, we're given that the block is in equilibrium, and what that means is that the sum of the forces on it is going to be 0. That means that this force is going to be pulling to the left just as hard as this force is pulling to the right. And that allows us to write that K1d equals K2 delta X2. And so then we can solve isolating delta X2 to get delta X2 equals K1 over K2 times D. Now remember that K2 equals 2K1, so this gives us delta X2 equals D over 2. So now for part B, we're asked how far will we have to pull on this side of the spring in order to stretch K1 to that distance D. And all that's saying is that as we pull this, if we pull a distance D, it's not going to move necessarily a distance D because some of that stretch is going to come from spring number 2. So we're going to denote this using a big D, and all that's going to be is that once we pull this to a distance D, we know that this has also been pulled to a distance D over 2, and so the total change from equilibrium length is just going to be D plus delta X2. Because obviously the block is not going to be stretching at all, and so the only change is coming from the two springs combined. And so that's going to be D plus D over 2, which is just 3 times D divided by 2.